Hello, everyone. Thank you for attending today's webcast, which is titled Legionella and Hot Water, Balancing Health and Sustainability. I am Christoph Lohr from IAPMO, the moderator and first speaker for this session. We'll start this webcast with a few housekeeping announcements and then quickly move on to our speakers, followed by time for Q&A, as well as a time for Zoom and some networking post this event. As a reminder, your screen is customizable utilizing the various widgets found at the bottom of your screen. Presentations can be downloaded as PDFs from the resources list in the menu. Attendees are in listen-only mode but can submit questions through the Q&A box anytime during the webcast. Partners or presenters will be answering questions following all presentations. All presentations will be available for on-demand viewing within a few days of the Engagement Hub. Zoom discussion will open at the end of the webcast to continue the conversation and allow for additional questions. Click on the Zoom widget or download the daily Zoom link PDF available on the Engagement Hub. Please be sure to fill out the form survey after your last webcast. It helps ACEEE in planning the future for future forums. ACEEE would appreciate your feedback regarding this year's Hot Water Forum. You'll have access to that survey link in all of this week's sessions on your console. Please take a moment after you watch your last webcast and complete the survey. For those that do, you will receive a $25 discount off your registration for the 2022 Hot Water Forum in Atlanta. Last, we want to thank our sponsors and partners for their support in the Hot Water Forum. And now I'm going to introduce our speakers. They are Christoph Lohr, myself, professional engineer, certified plumbing designer and lead a PBD plus C, along with ASSE 12080. And then my friend Scott Wolber, who is the director of engineering for Liquitech, and I believe he also holds his ASSE 12080, if I do believe that is correct. Scott, you can tell me if I'm wrong on that. We'll start with our first speaker, who again is me. I have over a decade of experience in designing plumbing systems. My current responsibilities as Vice President of Strategic Initiatives for IAPMO is to identify long-term, high-impact projects and bring resources to bear. I'm involved in multiple professional activities, including the American Society of Plumbing Engineers Legionella working group, which is creating a design guideline for plumbing. I'm actually the chair of that committee, along with a number of ASHRAE committees, such as 514-188. And I was also involved in the IAPMO Safe Building Reopening Best Practices document, first as a volunteer and then as staff. So my session today will be on hot water and Legionella, again, balancing public health and sustainability. If you have any questions as well post-meeting and you want to network or connect with me, by all means, feel free to reach out to me. There's my contact information, and that'll be shown on my last slide as well. All right, so for today's discussion, talking about hot water and Legionella, balancing public health and sustainability. And there's a little bit of a play on words here, as I'm going to be focusing a lot of this conversation today on hot water return systems, which includes balancing valves, and hot water return system design considerations. We're also going to touch base on some of the latest codes, standards, and just trying to understand the better context of how hot water return systems can potentially promote Legionella growth, but also how it can help properly reduce the risk of Legionella growth. All right, so when we talk about plumbing systems and we talk about the contributing factors for a Legionella case, the plumbing industry as a whole generally talks about the things that are above this blue line. So things like water age and disinfectant residual, temperature is especially one of those considerations, and aerating distal sites. Those are kind of the big three things that everybody in plumbing talks about. But below the surface, I guess that's just the tip of the iceberg. Below that, we have a whole set of criteria that includes water quality, things like nutrients, turbidity, surface area, which turbidity and sediment can help promote, but also oversizing of piping. All of that can create an additional hazard or additional risk as you can have more locations for the bacteria to grow. You have things that can impact disinfectants, and that's what all these arrows show is. It's kind of a sampling of the various ways that all these different criteria have an impact on each other. So, and that's what makes dealing with Legionella a very complex issue. It is not something that's simple. It's worth understanding that we have numbers of variables that all have an impact, and that they all have a impact on each other. They're all related. And so what that leads to is sort of a spectrum of risk measures or risk reduction measures. So this is sort of an example, sort of a mental model, if you will, to try to understand this better. We know of things on the far right hand of the spectrum that will increase the risk of Legionnaire's disease outbreak, such as long dead legs, stagnant water conditions, hot water, generally between the temperatures of 68 to 122 degrees Fahrenheit, especially if you start approaching 100 degrees Fahrenheit. That's the prime growth range for the bacteria. But we also have things on the prevention and control side. A lot of those are supplemental disinfection modalities, things that actively kill the bacteria, things like copper silver ionization, UV, chlorine, chloramines. There's a lot of things that will have an impact on the number of bacteria. But then we have things in the middle, and that's kind of part of this perhaps risk reduction or non-risk increase sort of spectrum of results. And that's things like hot water that's over 122 degrees Fahrenheit. We generally, hopefully everybody's seeing my slides here. Just got notes, just asking about the slides not advancing. So I just want to, hopefully that is occurring. The hot water temperatures, as we go over 122, there's these series of charts that have been provided that talk about water at 140 killing the bacteria in 32 minutes, water at 160 killing it instantaneously. What we need to realize is that is in laboratory conditions. Let's see here. Yeah, okay. The laboratory conditions basically is the bacteria with no biofilm around it, no scale, nothing that's kind of preventing the transfer of heat to the bacteria, which can occur. Biofilm can also protect the bacteria from some types of supplemental disinfectant. There was actually a study that was done that showed in a couple of hospital systems, so not laboratory conditions, but hospital systems, that the bacteria that was located in biofilm could survive over an hour in biofilm at 106 degrees Fahrenheit. So again, temperature is one of those things, depending on the water quality, that can get affected. Splitter valves, things that promote flow, bringing the flow closer to the plumbing fixture. That's something that can go ahead and potentially reduce the risk. But if your water quality is not good, then maybe it doesn't help you impact it as much. Filtration, again, if we're removing large particles, that can have an impact on disinfectant, on a number of things. So greater than 1 micron, we're reducing the amount of surface area and things that chew up the disinfectant. By itself, it won't necessarily eliminate the risk or prevent and control risk, but it'll help. And there's a lot of thought processes on, if we overlay, a multi-barrier approach or overlaying multiple technologies with each other, multiple approaches, that we can get a really good risk reduction or perhaps even achieve prevention and control in the grand scheme of Legionella risk reduction. So just wanted to try to give you all that kind of general framework before I dive into some of the specifics on hot water return. All right, so the first thing is when we talk about hot water systems, and this is one of those interactions between everything, is we need to understand with hot water systems that, especially as we elevate hot water temperature, specifically talking about copper piping here, that velocity becomes a key component. And from the Copper Development Association, right in their handbook, as you exceed 140 degrees Fahrenheit, because there's been a lot of guidance, such as in Illinois that had the Illinois Department of Health, which had mandated 106 degree Fahrenheit water temperatures in all buildings. There's a concern there because if you just go ahead and increase the water temperature to 160, the hot water return system, which may have been designed for 4 to 5 feet per second, based on copper piping, you need to slow it down to prevent erosion corrosion. So you slow that velocity down to 2 to 3 feet per second. That means that your flow rate decreases, which means that your temperature drop through your hot water system, both supply and return, increases. So you may have had a 10 degree delta T before, when you were at temperatures below 140, but once you exceeded 140, you may have a temperature drop of 20 degrees, which could mean you end up in the same or worse spot potentially. So we need to be mindful of that, that as water temperature increases, it becomes more aggressive. And so we need to slow down the velocity. So, there's a number of things we can do to slow down that velocity. One is decrease the flow rate, but the other one is to increase the pipe size. But as we'll talk about here in a moment, as you increase pipe size, your heat losses through your pipe increase because the surface area has increased. So there's always this balance point that we have to find between all those various components. All right, so why do we have hot water return systems? And this is kind of the first question. A lot of times, I think there's a little bit of we seem to have sort of forgotten as an industry, as a society, why we have hot water return systems. The entire point of a hot water return system is to basically bring the water heater as close to the fixture as possible. Older rules for older energy codes required basically if your water heater was more than 100 feet away from your distal site from your plumbing fixture, that you would have to have a hot water return loop. That's since been reduced down to 50 feet. And then other standards are further reducing that, or other codes are further reducing that. In some instances, for public lavatories, there's interpretation that you have to have it within 2 feet. But in essence, the point of having hot water return systems, especially in commercial buildings, especially when you have the water heater further away, is to prevent waste. Because as we know, heat goes from a place of high heat to low heat, or high temperature to low temperature. And so in an effort to achieve equilibrium based on physics. So we have hot water return systems to minimize the amount of energy waste of heating up hot water and then just letting it cool off and then discharging it to the drain. So the point of a hot water return system is not to circulate 100% of the flow at this time. It is just to maintain a given temperature in the loop. And that's an important delineation because there's been a lot of efforts over the last several years to turn on and off the hot water return pump. Now, in some building types, such as a retail space, generally speaking, I don't see personally, my personal view on this is an issue with that. However, for a hospital, there's a big concern when you have multiple branches and loops. There's a potential to have short cycling of the various loops. And that is something that needs further research. When a plumbing engineer goes through and designs a hot water return system, in essence, what they need to do is they have to take these series of equations that you see up on the screen, and they have to solve for multiple variables. Now, the problem is no one equation here can solve for another equation. This is not where you have multiple, two equations, two variables, and you can use the one equation to solve for the other. You have more variables than you do equations, which means you have to use a process of iteration. You have to make an assumption for one of the variables and then solve through these series of equations to figure out what your answer is, and then see if that seems reasonable based on limitations, such as velocity or pipe diameter or head losses, because head loss and flow rate impact your pump size. And then you have to go back through the series of equations again. The items here highlighted in green are things that we don't know. These are variables that we don't have, we have to solve for. The things in light blue may be known, but may need to change. And that's why we have so many variables. This process is known as the Hardy-Cross methodology. And this was something that I learned in my senior college class. And what's been interesting to me during the decade plus that I was doing engineering consulting, it seems like a lot of that methodology was not taught, at least to the young engineers that I was mentoring and training at the firms that I was working at. In essence, this is per Michael Lindbergh, who wrote, I have his 12th edition of the Mechanical Engineering Reference Manual sitting on my bookshelf behind me. But in that document, he talks about how network flows in multi-loop systems cannot be determined by any closed form equation. Most real-world problems involving multi-loop systems are analyzed on a computer. Think Excel or a computer program, if one was available. Computer programs are based on the Hardy-Cross method, which can also be performed manually when there are only a few loops. In this method, flows in all the branches are first assumed, and adjustments are made in consecutive iterations to the assumed flow rate. So again, you start with flow rate and you iterate from there as the Hardy-Cross methodology, which is what I learned in my senior year of college. But much of industry has seemed to deviate from this for any number of ways. So we just need to be mindful of that process. All right, so why does this matter? Again, if we have this simple loop here, assuming that the pump symbol down here in the bottom right-hand corner with the inlet pipe, that represents our water heater, recirculation pump, and mechanical room. we need to have, the situation, in this system, we're trying to maintain flow rate for our A, B, C, and D loops, respectively, going from right to left. Now, we add balancing valves, shown there after each plumbing fixture, to basically create an artificial pressure drop. Why? Because as we all know, water is lazy. Water will take the path of least resistance. And if we don't have some kind of restriction there, the water will flow through the closest loop. It will not go through the most hydraulically remote loop. Assuming this was to scale, that would be the D loop. So we add an artificial pressure drop, so artificially lengthen the pressure, the piping, if you will, through the A loop, B loop, C loop, and D loop. Now, one of the problems that we have is when the plumbing industry for a very long time has used what I would call manually adjustable balancing valves. These are valves that have a plate on the side that indicates CV value. So CV should not be confused with GPM. The equation here at the top on the upper left shows that representation. Again, specific gravity for water is 1. So again, for the most part, is negligible. But as the CV is adjusted here, the pressure, the square root of the pressure change, and the GPM are related to each other. There's a difference there. What's worth noting, though, is going back to our previous example, as that dial is changed on this A loop, we can get down to, let's say we had a 4 GPM pump, right? We wanted 1 GPM through each one of these loops. Well, when we get this A loop to 1 GPM, we come over to the B loop with that manually adjusted balancing valve. What happens, though, is when we get to this B loop to 1 GPM, what we have to realize is that the A loop is no longer at 1 GPM because we've changed the pressure based on that equation. So we have to go back to the A loop and make that 1 GPM. But now the pressure is impacted here. And so the test and balancer will go back and forth between the two. Conversely, when they get to the C valve, they have to go back through and rebalance all of those. I can tell you from personal experience, during the course of my over a decade doing plumbing engineering design for hot water return systems and dealing with construction, I had exactly one instance in my entire 10 years where I got a test and balance report on a hot water return system. And it is not uncommon for even the largest buildings to not have this done. It's a very big problem because now not only are we, based on the energy code where we're turning on and off a pump, that we are also potentially having under normal operation when the pump is on, a short cycle condition in the plumbing system. And so it's very key for us to understand that. So for balancing valves, my personal opinion is that test and balancing should be a requirement, but also commissioning to validate that the testing and balancing occurred. Now, since in the last 10 plus years, I've seen a number of valves come onto the market. I have dubbed these automatic balancing valves, and there's 3 general categories out there. First is pressure-independent balancing valves, both fixed cartridge type and adjustable. There's thermostatic balancing valves, both fixed cartridge or adjustable. And then now coming onto the market in the plumbing sector is electronically actuated balancing valves. Now, from a hydronic standpoint, a lot of these valves have been out there, but from a plumbing standpoint, because of the Low Lead Act, the hydronic valves can't be used. We have additional requirements for water because we don't drink hydronic water, we drink potable water, which is the systems that we're talking about here. So each of these types have their own strengths and weaknesses, and we just need to be mindful of these. Now, the benefit of these automatic balancing valves is, my sense is, in general, they don't require testing and balancing because they automatically balance it. However, we still would want to see commissioning done just to validate that the flow rates that were specified and designed were actually what we were seeing in the system. Pump selection also becomes important here because pump selection can have an impact on your overall system. I've seen plenty of plumbing engineers over or undersize their hot water return pump, going often back to the pump that they always use, even if their building is, has 20 more loops than their normal building. One of the things I would encourage plumbing engineers to do, and that I often do, is if their building is highly variable, like a hospital, utilize a variable frequency drive pump that has a manual set point for both flow and head, and dial that in. Now, there's some considerations for hot water using variable speed drives in conjunction with thermostatic balancing valves, either fixed cartridge type or automatic or adjustable type. That is something that I want to do a little bit more research into. I think there's a possibility there. I think there's a very strong possibility, and I think there's been a lot of successes, but I want to see the mathematics work out on that. So if anybody has some of those mathematics, please reach out to me. Would love to have that conversation. I definitely would love to learn more there. All right, there are some lessons that are learned, and it's things that I've seen during the course of my career. One is the one that's most common that I've seen is healthcare plumbing engineers and high-rise plumbing engineers having different understandings of multi-zone hot water systems. This is actually taken from a project that I did the quality control on a number of years ago. And in essence, we had a water softener, a booster pump, and a water heater, and we had about 50 PSI coming in. And the water basically was up to 100 PSI in order to reach the top floors. There was also a central sterile processing department that needed a higher pressure. And so 100 PSI was coming out of the booster pump. They had a line going to the water heater, and then out of the water heater, they had a pressure reducing valve for the lower floors because code mandates no more than 80 PSI. So they had 80 PSI for the lower floors, and then floors 3 through 7, the higher up floors, they had a high pressure line. What was interesting, though, was on the way back, each of those systems had a hot water return pump, and then they tied the line back to the water heater. This was something that I marked up. This is a no-go. Why? Because if you have 80 PSI and 100 PSI going, assuming no pressure losses through the water heater, you're at leaving the water heater. When it comes back down, assuming minor, friction losses, you're going to have about the same coming back due to the weight of the water. Well, even with the check valves and everything else associated with the hot water return pump, what happens in this situation is that hot water return pump 1 is going to deadhead. It is not going to have much flow because the pressure coming out of hot water return pump 2, because of the weight of the water coming back as it comes around, would cause no flow for floors 1 through 2. This is something I've seen time and time again. There's a problem. The solution to this is something that I learned from a colleague on hot water or high-rise design, which is to create multiple pressure zones. So this is obviously a much taller building than the 7-story example that I had before. But in essence, you have a water heater and an express riser that you see here on the right. Then you have a pressure reducing valve station that taps off, very short length. You can get that with 5-10 feet at the most. And then you create sort of a reheat heater that includes a recirculation pump for that zone. And that reheat heater basically takes care of the temperature drop within that zone, while the main heater takes care of the makeup for any hot water that is used by the various tenants or people or occupants in those various spaces. And this is very common in high-rise design. All right, again, because of these concerns, when we shut off the recirculation pump, I have very big concerns about this. And this is something that as an industry, we need to take a closer look at. I know a lot of engineers that ignore this requirement for healthcare or other spaces that fall under Legionella because of the concern of balancing issues and then worrying about short circuiting and not achieving temperature, the temperature that is the design temperature at the most hydraulic loop. So plenty of engineers that I've spoken with basically ignore this requirement for healthcare, hospitality, and other buildings that fall under ASHRAE 188. So this is something I think as an industry we need to go back and reevaluate. And that's my personal opinion on that. All right, finally, it is worth noting that there are a number of codes and standards that are coming out that are focused on plumbing resiliency. It's worth noting the WELL Health Safety Rating Index and WELL is having this focus on well-being within buildings. AWWA and IAPMO, we are about to release a manual of best practices for the safe closure and reopening of buildings dealing with water systems. There will be a section in there that deals with construction. Again, I mentioned my involvement with ASPE. There's a Legionella guideline that will be coming out hopefully by Q3 of this year. Should be released at the beginning of Q3 for public review. Would love to have your input on that. A lot of these have things that talk about hot water and the concern of circulation. The manual of closure and reopening actually will include sections on construction as well. So again, will be worth noting. And there's just going to be a lot of information coming out into industry that deals with this topic of hot water and taking a more holistic approach to that. And so we need to be mindful of that, as we do design, as we provide recommendations. Again, does it apply to every building out there? I would argue no. Again, we're looking at buildings with immunocompromised populations, hospitals, long-term care, apartments, and condos, certainly, because you could have elderly folks and people that are immunocompromised living in those buildings. But generally speaking, an office building or a retail space, the possibility of exposure or the potential of risk of contracting Legionnaires' disease or another waterborne pathogen is much, much lower. So we need to, this doesn't necessarily apply to all buildings. Again, I'm not trying to say that, but we need to be a little bit more selective in thinking about how these design measures apply. So again, just a quick summary of what I spoke about today. Again, my contact information there. If any of you want to reach out, please do. I'm also on LinkedIn and Twitter. Twitter handle is @LoreThoughts, all one word. On LinkedIn, you can find me at Christoph Lohr PE. If you look me up, that ugly mug of me, you'll see my face there, and would love to connect with any of you in that regard. All right, moving on. Our second speaker is Scott Wolber with Liquitech, who's their director of engineering. Scott has been involved in over 1,000 Legionella control projects and has extensive experience in hot water return system evaluations. One note before our speaker starts, IAPMO does not endorse any specific products or manufacturers. You will notice my name on a few of Liquitech slides, and that is because I worked for Liquitech until October of 2020. And the white paper that is referenced in the Liquitech presentation was produced by me during that time of employment. So just want to make sure to make that disclaimer before we jump over. But I will now turn this over to my friend, Scott Wolber. And if you want to take over here, Scott, we'll have you move forward.
Yeah, absolutely. Thank you, Christoph. Thank you, and thank you for the warm introduction there. So kind of just jumping ahead here, on the agenda for today, we've got this presentation broken out into two sections. Section one is going to be talking in a majority on the effectiveness of higher hot water temperatures in killing Legionella and all the waterborne pathogens. We're going to touch on some of those engineering considerations and expand a little bit on what Christoph touched on earlier. And then we'll round out that section with the economic implications of the higher hot water temperatures. And section two, what I'll do is I'll introduce an option for you guys to not go with a higher temperature hot water system and instead use something more systemic. So it's important to start at the beginning when we're talking about high temperature and Legionella control. Traditional hot water system design methodology has been to set a water heater at 140 or 120, and with newer systems coming out at 160, and then mixing it down to 120 to reduce the risk of scalding. So these increased water temperatures aren't really what I would term a control measure, and it should only be considered a risk reduction method. It's worth noting that the temperature ranges commonly accepted by the industry are based on only laboratory conditions. The ranges do not account for biofilm or scale and contact times needed to kill Legionella. Scale and other biofilm acts as insulators of bacteria, meaning that higher temperatures may be needed for longer periods of time in order to kill the bacteria that we're targeting. There are many incongruencies between industry recommendations in regards to hot water temperature as a control measure. Rather, hot water temperature should at most be considered a risk reduction method, but not a full control measure. And any language implying cell death at hot water temperatures below 140 degrees is not supported by any field test. It's really important, and I want to highlight that. The correct assessment is that regrowth risk is reduced below 145. And the standard industry range chart is a very simplified portrayal of a very complex problem. And that chart's shown here on the left-hand side. So in essence, it's very impractical to take this chart, which has really infiltrated the industry, and take it to heart and say, oh, if I heat my water to 160, I'm going to be killing Legionella. On the bottom of the slide there is an excerpt from a study that shows contact times required to reduce the mean viability of cells for Legionella. So you can see even with 60 minutes of contact time with 160 degree water, 158 degree water, 70 Celsius, there is still viable Legionella. So like Christoph mentioned a little earlier in the presentation, scalding is a major concern when you're elevating water temperatures beyond 120, and you've got to bring that water temperature down so that you can actually serve it to building occupants. So on the slide here, I've got 4 graphics that were built to kind of show how these temperatures interact and how the water temperature plays with the control or the high temperature kill ranges for Legionella. So the first one on the top left, water comes into the building and is brought up to 120 degrees Fahrenheit at the water heater, and then it's distributed out through the building where it starts to taper off, and Christoph mentioned that temperature loss throughout the building. Number two, water coming into the building is heated to 140, distributed, and then mixed down by a point of use thermostatic mixing valve at the final distal site. Number three, water coming into the building and heated to 140, and then it's reduced to 120 via a master mixing valve, and then distributed throughout the building. And the final one is the final iteration that I've seen out in the field is water comes into the building and is heated to 160, reduced to 140 via master mixing valve, and then finally reduced down to 120 at the point of use. The main thing I want to highlight here is that there is not a single configuration on this graph which shows no water in the temperature growth zone. My saying is, when you mix, you lose. So anytime that you mix, you have to mix water down, you're going to be back into that Legionella growth temperature, and you're going to lose the control that you thought you had. Going to go over a couple of 160-degree hot water design considerations today. I'm going to touch on the top four, the four that I think are most important in my experience and the things that people really care about. Christoph touched on a couple of others. Some of them that I won't be covering today: increased demand on the plumbing infrastructure, and Christoph touched on that with the hot water recirculation and flow rates. He also touched on the recirculation pump size, velocity limitations, and pipe size, and the final one, oxidizing agents. Anytime that you increase water temperature, you're going to increase oxidizing agent burn-off, and you're going to reduce efficacy there. So I'm going to touch on 1 through 4. And the first one I'll touch on today is the heating capacity. So assuming a consistent amount of water is needed and incoming water temperature is 40 degrees Fahrenheit, depending upon where you're at in the country, this is true for a lot of locations, and the water heater is set to 120, the multiplication factor to increase that water temperature up to 120 is 80 degrees. That's an 80-degree temperature delta. However, if the water heater is set to 160, we are now having to increase that water temperature 150% over that original configuration. That means that instead of potentially needing 4 water heaters, I now need 6. And that generates directly to energy costs and directly to building costs when you're designing these structures. The second thing I'll touch on today, 160-degree hot water design. One of the major things that I see out in the field is a lack of respect for insulation requirements when it comes to elevating hot water temperatures. So per the IECC, the 2018 code, which I've got an excerpt here on the slide, anything over 140 degrees will probably need 1.5-inch thick insulation, and that's to prevent the temperature loss as that water is being distributed throughout the building. Christoph touched on that quite a bit, and I'm going to highlight it again here. Anytime that you increase water temperatures, you're going to need extra insulation. This is imperative for retrofits when an older infrastructure is going from 120 to 140 or 160 degree water distribution. Most of the time, the insulation is just not adequate to keep that water temperature hot. And that's going to tie back into your control measure, or what you're attempting as a control measure with your temperature. When you lose that temperature out in the distribution system, you are losing the ability for that temperature to actually kill the target bacteria. The next thing I'm going to touch on, and I mentioned it earlier when I was talking about the mixing valves, scalding. I mentioned you cannot serve 140 or 160 degree water to building occupants, and we all know that's very true. At least I would not want to interact with that personally. So anytime that you use a high temperature regimen, you've got to use a point of use or a master mixing valve, thermostatic mixing valve, and you've got to implement those across the building. Every one of those point of use mixing valves can be upwards of $100. And so when every fixture needs one of those, the costs stack up very, very quickly. Additionally, my field experience has granted me the knowledge that these devices fail very regularly. Some of the failures are correlated to water hardness or other water quality parameters, but I can tell you that most of the time, I'm very surprised if these thermostatic point of use mixing valves last anywhere longer than 3 to 5 years. I've ran in personally to facilities that have only had them last a year before they have to be replaced. That ongoing cost is something that needs to be taken into account and factored for when infrastructure is being designed. The final one, a big one that I see in the industry in water quality nationwide, worldwide, is lead release. So lead service lines are a big topic in today's water quality discussions. I'm going to highlight this here. Anytime that you increase water temperature, you're going to increase leaching of the base metal, and that's because that water is now more aggressive in its corrosion characteristics, and that applies to the lead that may be in that plumbing infrastructure as well. So anytime that you're going to increase water temperature, you're going to increase the lead release of the base metal. The final one I'll touch on here today, and I know this one's a big one when you're talking about energy consumption scale. It's one of the more insidious things in a plumbing infrastructure and really can wreak havoc with water heater efficiencies and distribution efficiencies. Scale forms more readily in hotter temperatures. So anytime that you increase the temperature of water, you're dropping the solubility of that water, and you're allowing that scale to form more readily. That scale drops your heater efficiencies, like I mentioned. But the big thing that I see is on hot water return lines where there's a precipitous amount of scale on the interior of those lines, those hot water recirculation flow rates actually drop because of the increased pump head on those systems. So you may design a building today that's got 10 gallons per minute recirculation flow rate, and then in 5 or 10 years when that scale has grown, that return flow rate may be half of that. And that's something I see all the time. Kind of touching on the economics here, just kind of rounding all of these economic discussions out. Jumping up from 120 or 140 to 160 is not something that you can just flip a switch and do. There's a lot of components that have costs associated with them and a lot of things that have to be taken into account. Christoph touched on the plumbing size. I talked about insulation, water heater capacity, potentially a larger recirculation pump to make sure that you can serve that higher temperature reliably throughout the infrastructure. And then finally, I touched on a lot of those mixing valves that you've got to have, either master mixing valves in the mechanical room or point of use mixing valves out in the infrastructure next to the distal locations. All those account for higher costs. So Christoph talked a little bit about some of the piping costs, just continuing to kind of round out here. When we go from 120 to 160, just some back of the napkin math, copper prices increase by about approximately 150%, and that's due to the requirement of having larger pipe diameters to handle that higher temperature. Remember, Christoph mentioned that anytime that you increase the water temperature, you're going to need to either slow your recirculation flow rate down, which it really isn't not advisable most of the time, or alternatively, you're going to have to increase your pipe diameters, and that directly associates to cost. Anytime you've got to jump up to that thicker insulation size, your insulation costs are going to increase. Again, back to the napkin math here, 186%. And your water heater cost would then correspondingly increase 150% based on that example that I provided earlier, going from 4 to 6 heaters. Continuing out some math here, we analyzed a couple of different facility sizes. When you're talking about a healthcare facility, so a 50-bed, a 250-bed, and a 500-bed facility, we made some assumptions based on a 55-degree cold water inlet temperature, gas water heaters. We made some assumptions based on the building size. And what we ended up with really raised my eyebrows when we finished calculating it out. So to go up to 160-degree water temperature in a 50-bed facility, we estimate that the additional cost to do so would be just under $210,000 for that facility. It goes up even worse when you talk about a 250 bed, just under $900,000, and on a 500 bed facility, just under $2 million. So when you're taking into account the competitive scenario that is healthcare today, when you add these additional costs into your facility or your building design, it's something that you really have to pay attention to and think consciously about when you're making these decisions. Going to go into one of the other options. Up to this point, it's been really doom and gloom. Essentially I've been saying don't use 160-degree water. There's a lot of problems with that, but there are other options on the market, and I'm going to go over one of those options today, and that is copper-silver ionization. So copper-silver ionization is the most effective non-chemical potable water treatment available. It's safe and easy to maintain. There's no corrosive or harmful disinfection byproducts. It's got an extraordinarily long residual protection, meaning when I put it in the water, it becomes systemic. It gets distributed throughout the building and makes its way to all the distal sites, all the points of use, and disinfects all the way to the end user. One of the other hallmarks here directly correlating to this presentation is the opportunity to reduce heater temperatures from 140 degrees to 125 degrees. That corresponds directly with LEED initiatives and other energy-saving conservation initiatives. This technology, it sounds a little bit like black box magic, but I can assure you it is ran the gauntlet with scientific and peer-reviewed studies. In fact, copper-silver ionization has the most peer-reviewed studies of any Legionella treatment and control methodology. And finally, Liquotech's copper-silver ionization has maintained a US EPA registration to make claims of eradicating Legionella in drinking water. So there's a lot of advantages when you're thinking about transitioning from 160 or 140 degree control scheme to an alternative technology such as copper-silver ionization. Just going to go really quickly into how it works. Step one, water passes through a device that we call the flow cell. It's the actual ionization chamber. This is where we generate the ions. Step two, direct current is applied across the electrodes, creating positively charged copper and silver ions. The ions are then released out utilizing the flow through the ionization chamber and distributed throughout the facility with general water use and water recirculation. So those ions actively seek out and attach themselves to bacteria so that they can actively kill it and control it. A little more on how it works. The positively charged copper and silver ions are actually attracted to negatively charged bacteria. The bacteria that we're talking about, predominantly Legionella, actually has a negative charge on the surface of the cell wall. The ions that the copper-silver ionization system produces are actually positively charged. So there's actually an electromechanical charge pulling those two pieces of matter together and bringing the copper and silver ions into contact with the bacteria so they can so that copper can weaken the cell wall, and then silver can then infiltrate it and cause cell lysis or death. One thing I want to note here, contact time is crucial to bacterial death. You've got to give these ions time to work, and that's the same for any other disinfectant on the market today. Couple of different iterations that you can install copper silver in. What I've shown here on the screen is a single flow cell hot water installation. So generally this is going to be installed on the hot water return. Water is going to come back from the building, pass through the pumps, and then on its way to the heater, it's going to pass through the ionization equipment, and then it's going to continue on going to the heaters for reheat. This is the generation point for those ions, and we're using that hot water recirculation as a mechanism for distributing those ions throughout the entire infrastructure. Another option we've got is of how you can install a copper silver ionization system is installing on the point of entry. And this is in a side stream application where a small amount of water is diverted off the domestic cold water coming into the building, passed through the copper silver ionization system, and then reintroduced into the domestic cold water. One thing I want to note here, right inside that schematic on the top right-hand side, you can see that there is a a small device there attached to the pipe. That's actually a flow meter, and that's something that I would recommend you think about if you're going to specify one of these, making sure that it's got that device on there. That device actually talks back to the copper-silver ionization system and proportionally doses the amount of copper and silver being introduced to the system based on water demand. It's a very, very important aspect of the technology and something that you should be sure to not overlook when you're thinking about this. The main thing on everybody's mind is efficacy. How effective is this stuff? Like I mentioned earlier, copper-silver has an enormous amount of peer-reviewed studies on the table that you can review. You can Google Legionella, copper-silver ionization, and you'll be inundated with data. I highlighted and pulled out a couple of different things here. E. coli, Listeria, Salmonella, Pseudomonas, Bacillus anthracis, Legionella acinetobacter, Mycobacterium avium, and Stenotrophes multifida, which is one of my favorite words to say. You can see that copper-silver ionization has a very effective and high percentage of microbial kill when we're talking about these organisms. And I want to tie this back to some of the difficulties that I highlighted earlier with temperature control schemes. Temperature has difficulty controlling those bacteria in the distribution system all the way to the end user. And when you compare that to the data that I'm showing here, it's very advantageous to be thinking about alternative technologies. So in conclusion, heating to a higher water temperature such as 160 should not be considered an effective way of reducing Legionella. And in fact, by reducing water temperature to 120 from 160, you can get rid of having to do a lot of considerations that would otherwise be required, such as the insulation, the pipe size, the water heater, and all those associated costs. That increased cost is not justified by any measure when you're talking about actually controlling incidences of Legionnaire's disease, and considering that alternative treatment methodologies such as copper-silver ionization can come in at a much lower cost when comparing to all those infrastructure requirements. It's definitely something that I would recommend taking a look at when you're doing your water system design. And that concludes my portion of the presentation. And I think that concludes both Christoph and I's portion. So I think we will move into Q&A. And I think the Zoom portion of this does not open for another few minutes till 1:45 the hour. Do I have that right, Christoph?
I believe so, yep. That does conclude our two speakers. So thank you, Scott. Again, that was a great presentation. Now we will hear from our audience, and we'll go ahead and take some questions here. So the first question that came in, actually there was a few questions on this, was talking about water heater capacity, and just kind of trying to get an idea of how water heaters are sized. So I'll take a first crack at that, and then Scott, if you want to add to my answer. But trying to figure out sizing water heaters and how that plays in as you increase temperature. So most of the plumbing industry utilizes a formula from the American Society of Plumbing Engineers for water heater sizing. And in essence, that is determining a total gallon per hour based on a total number of fixtures, and each fixture having a minimum requirement for gallons per hour. And that there's some in the ASPE handbooks that's delineated by building type. So, a hospital will have a different gallon per hour for a faucet than a hotel will. And that's just based on typical, observed behavior of occupants in those different types of buildings. And so when we look at water heaters, so let's assume we're going to maintain a given size water heater, right? And let's say the owner has a standard, or you have a maximum size of water heater. So if you're using, let's say, a tankless type of water heater, which is very common in a lot of hotels here in the Southwest. If you have your water heater on, let's say you had needed 10 of them to serve, this building, you're going to have them all sit on the roof based on the total gallons per hour that's needed. Well, one thing we have to keep in mind is that gallons per hour on the individual water heater manufacturer's devices for a given size, assuming a constant size, assuming let's say 199, the gallon per hour value will reduce as the as the temperature differential between the incoming water temperature and your output temperature from your water heater increases. So again, as your water heater heats up the water to a higher temperature, you will have less gallons per hour available from the water heater. And so, so when we're designing or selecting number of water heaters, again, assuming a constant, let's say 199 water heater, and you don't want to change the size based on limitations from the manufacturer, as you increase the water temperature, you're going to need more BTUs to increase the hot water temperature. And so that will correlate to more water heaters. Scott, anything you want to add to that?
Yeah, when I kind of just think about water heater capacity, water heaters in general, if you oversimplify it, they are rated for a certain degree of temperature rise per gallon coming through them. So when you want to increase temperature, like we described, going to 160, the end result is ultimately that you're going to need more water heater capacity. So I definitely agree there is a lot of intricacies in water heater system design and water heater sizing, but the end result is when you increase temperatures such as that, you're going to need more water heater capacity.
Right on. All right, next question that came up. How is copper silver ionization affected by water temperature? I think that one is for you, Scott.
Sure. Yeah, so unlike other chemical oxidants that are available on the market today, you're not going to be witnessing what I call oxidant burn-off with increased temperatures. The important thing to keep in mind when you're dealing with any oxidizing disinfectant is that when you increase temperature, you're increasing the chemical reaction in which that oxidizing agent actually oxidizes. So when you increase temperature, you're going to increase the rate of burn-off, what I call burn-off of that oxidizing disinfectant. When you're utilizing a technology like copper silver, what you're introducing into the water is metallic ion, and that ion is not affected by temperature in the same way.
Awesome. Next question is, both presentations were on commercial systems. Any thoughts on Legionella and residential? Great question. What I would say on my side is, and again, Scott, if you want to chime in afterwards, but generally speaking, we worry about complex building types where you have very intricate plumbing systems, multiple parallel branches. There are instances, actually, I remember reading a case about a birthing tub here in Phoenix being linked to Legionnaire's disease in an infant, a newborn infant. But generally speaking, residential systems, if you're living in a house, you're flushing it out. Now, if you have a cabin and or a timeshare, let's say, that hasn't been used, definitely some concerns there. And so, from a multifamily, otherwise, or apartment type of building, there's some concerns there. But because those buildings are typically lived in and there's much more usage, as opposed to, let's say, a hospital where sometimes you see less water usage, like we did during COVID. Typically residential is a lower concern, but it is still possible. Scott, anything on your end?
Yeah, some of the primary risk factors for Legionella amplification in plumbing systems, the first and foremost is that there's a higher incidence of Legionella amplification in plumbing systems that have a hot water recirculation system attached to them, because like Christoph just described, those are much more complex infrastructures, lots of high surface area to water ratios, where you've got lots of places for that bacteria to hide out and amplify. And the second kind of thought I've got on that is really correlating back to risk factors for adoption or infiltration of the Legionella bacteria into a susceptible host. Most of us in our homes or in residential properties, we are of a high caliber of health, you could say, and we're not going to be immediately susceptible to that bacteria. That's in sharp contrast to immunocompromised patients in a hospital or other healthcare acquired setting.
Awesome. Next question. This one looks like it's for you, Scott. What is the typical cost of a copper silver ionization system? Also, does this type of system address dead leg issues? Asking about Legionella. I imagine also with the question on cost, imagine the person's also asking a little bit about payback potentially, if there is a payback in that regard based on the energy data you showed earlier too.
Sure, sure. So the typical cost of a copper silver ionization system, it really depends on the size of the building, and that's the engineer hat on. They tend to go anywhere from, say $50,000 up to $250,000, and that really depends on the manufacturer and what you're getting with that money. But that's kind of where your head should be at when you're thinking about that system. When you're talking about dead legs as a point of, I guess you could call it optimization, I always guide customers to seek out and remove dead legs if they know they exist. Obviously, in today's plumbing infrastructure, even with brand new buildings, I walk in and find dead legs all the time. And one of the advantages, like I mentioned earlier with copper silver ionization, is that it does have a very long and steady and strong residual when it's in a plumbing infrastructure. So while an enormous dead leg or a very problematic dead leg is something that should be isolated and taken care of, throughout my experience, you can oftentimes gain control with copper silver ionization, even with those structural impediments in your way.
Awesome. Thank you, Scott. Great answer. Very in depth. Next question. This is a question for me. So I had mentioned that we should think critically when adding controls, again, turning on or off a recirculation pump for hospitals and occupancies where there may be vulnerable populations. Do I have a sense of how common Legionella is in multifamily buildings, and would you expand your recommendation to all multifamily buildings? Great question. I think that came from Jack, so thank you for providing that. What I would say is generally when you look at the CDC data for Legionnaire's disease cases, it mostly comes from hotels. That's actually one of the, I think like 40-some% comes from hotels. And I think, Scott, you and I learned about that in our ASSE 12,080 class. And then hospitals and long-term care kind of follows suit. Multifamily, I think, is a lower percentage. And again, multifamily, you have people living in these spaces, and so the water's more frequently being utilized than perhaps in a hotel or other spaces. That being said, you could still have at-risk populations that live in a multifamily. You could have somebody over the age of 65. You could have a smoker. These are all people that live there that they could potentially, in theory, develop Legionnaire's disease from the water systems there, from the plumbing system. So, I think in my mind, they're at the very least doing testing and determining what the water quality is on a regular basis is a needed part. When I did plumbing engineering design, whenever I was involved in a multifamily, I always made sure to make the building owner aware that especially if they were a high rise, or if they had a shared water heater system for all the tenants, that they fell under the requirements of ASHRAE 188, and thus we should be doing something. Now, would it be necessarily a copper silver ionization system? Perhaps not. Maybe in some instances it would. That kind of came as a decision to the owner. But sometimes we took other measures, such as making sure that the hot water return pump was on, especially if it was for a centralized system. Maybe we added UV, maybe we added filtration. Perhaps we delivered at a higher water temperature. Maybe we tried to bring those hot water loops closer to the various fixtures. Again, we maybe did some of those things in the risk reduction, that middle ground, and depending on water quality, we could get it closer. But we also a lot of times put in provisions for emergency remediation measures too, and thought about piping materials. So yeah, definitely a lot of things we can do. Great question. Next one up, any issues with some of the piping materials, they say PP, by introducing copper silver ions into the water? I think that one's for you, Scott.
Yeah, sure. The only material that has a known incompatibility with copper silver ionization is PPR, and that is it's usually green in color, and it's the type of piping that is fused together with either an ultrasonic or a heat fusion process. It's mostly used internationally. I read a lot about this material being used in places like Australia. That material actually uses copper as a catalyst during the creation of the material, so it does have a known weakness to copper in water. Beyond that, there are no chemical or no incompatibilities with any plumbing material.
Awesome. And we just have a minute here before we have to jump over to the Zoom call.
Sure.
So next question is, hi, is it safe for everyone to be drinking copper silver water?
Sure.
So I think that's for you, Scott.
Yeah. First things first, the EPA does have limits set on how much copper you can put into the water, and that's under the lead and copper rule. The second one is silver. You've got an EPA secondary limit on silver at 100 parts per billion. If properly applied, no copper silver ionization system should even approach those concentrations that you're talking about for any concern.
All right, and last question, and then I'll save the other one for the Zoom call. One more follow-up question: what kind of maintenance cost is associated with a copper silver ionization system? I think that one's for you as well, Scott.
Yeah, sure. So monthly, there is a descaling activity where the flow cell is removed and descaled to make sure that the ion transfer is efficient. The other thing that I would recommend you make sure that is included is a monthly sampling of the actual copper and silver concentrations in the water system. And then finally, that's followed up with, I would recommend quarterly Legionella sampling to make sure that the program is validated and in control.
Perfect. I was going to say, it looks like we just have a couple seconds here. Is Legionella risk difference in copper pipe versus PEX pipe? So I will take this one. In essence, the only information I'm familiar with at this time is the Kiwa study, which looked at several different types of biofilm growth potential, which biofilm is what Legionella inhabits. It's kind of a food source. Almost think of it as like a hotel. That particular Kiwa study showed that copper piping, which was assumed to be among the best, as it came in contact with water, it lost its antimicrobial features and actually became sort of, I guess, average, if you will. And PEX piping right from the get-go, because of the sort of the porous nature of the inside of the pipe with a lot of crevices, on par with copper, with aged copper, that is.
Yep.
That particular study, which looked at CPVC, steel, stainless steel, and a number of others, found that stainless steel and CPVC were among the best as far as the lowest biofilm growth potential. Polypropylene was kind of in between the aged copper or PEX and the stainless steel and CPVC. But that's, again, one study, and that's one I believe that was in part came via funding from CPVC resin manufacturers, although don't quote me on that. I'd have to go back and look at that. Great questions. Well, that concludes this session. I just want to say thanks again, Scott. Thanks again, ACEEE Hot Water Forum, for this opportunity. Again, thank you for our attendees for participating in today's webcast. Again, if you'd like to continue exploring the topics with Scott or myself, please follow us onto the Zoom chat room at this time. Thanks all.
Thank you.